Hi there, welcome back to this channel. In today's video, we are going to be learning about the simple AC circuit. Now we have learned about, so far we have learned about the magnetic effect of electricity and how that electricity will be generated through a changing magnetic flux. So the kind of electricity we learned that could be generated in that process is one with alternating current or alternating voltage. I mean, if current is alternating, it therefore makes sense to say that voltage is alternating. Is that okay? All right, so what is AC? AC basically means alternating current. So we are learning about the alternating current circuit. Before we learn about it, let's talk about a brief history, very brief history about concept of alternating current. Now, during the early 19th century, there was an era that was called the War of Current. So during this era, it was typically about which method should be used to transfer power, basically then throughout USA, then of course all over the world. All right. So and the war of current happened between some prominent scientists, two sides. We had the proponents of DC circuit, the proponents of DC circuit, so direct current circuit, and the proponent was basically Thomas Edison. So the one who we attributed the discovery of light bulb to, and of course it was between him and two other scientists and inventor, Nikola Tesla and George Westinghouse. So some textbooks do not talk about George Westinghouse as a scientist, but basically an investor. So we majorly attribute the discovery of AC circuit to Nikola Tesla. All right. Now, so at that time, the war of current was between whether it was DC that was the most proper to distribute power, or AC. And of course, these two set of scientists were at loggerheads. And Thomas Edison said the direct current circuit was the best because it was easy to control, and that was his major argument. While the Nikola Tesla and George Westinghouse saw that AC circuit could be used to transfer or distribute electricity over very long distances, and that was because that was one of the major advantages of AC circuit, which was the fact that it could be stepped up using transformers. Is that okay? So typically in USA, about 25,000 volts of electricity are generated, and it is stepped up to about 132,000 volts. You understand? So you see how very far apart the voltage that is generated and the voltage that is distributed is. So it is stepped up using step-up transformers. So this was the major advantage that AC had over DC, and because of that, it could be transferred or distributed over very long distances. At high voltage, low current. So another thing was that it minimized loss of energy, because if it was high current, low voltage, that would cost more power. Is that okay? That would cost more. Is that okay? And DC also costed more. Is that okay? So another disadvantage that the DC current, according to them, had over the AC, the disadvantage DC current had was the fact that if DC was used, it means that there will be electric grid at every 10-meter drive away from houses. Is that okay? Because it couldn't go very long. Is that okay? So, but Thomas Edison said that it could not be curtailed. That is the power of AC. It could not be controlled. So, in about 1920s to 1930, Thomas Edison, Nikola Tesla was able to control the AC, or showed experimentally how that AC could be controlled. In one of the experiments I saw, I think it was so much that the power was passed even through, he wore a particular cloth, and the power was passed through him and out, and he did not die, just to prove that the power could be controlled. Of course, it was something like an insulator also. Is that okay? So, but the point is that these two guys, won the war of current, and so since then, every other part of the world have been powered using AC circuit. All right. So that is about the war of current, the brief history about AC circuit. So now we know that this guy, AC current or AC alternating voltage, oscillates between 2 points, the maximum and minimum point. So it makes sense to represent it using a sinusoidal graph, because that is basically a simple harmonic motion oscillating between minimum and maximum value. And let me show you what that means. So if I had my circuit like this, and it was connected in series to a load. Now what this means is that current is running from positive to negative, negative to positive. Not really negative to positive. Positive and negative are oscillating around here. They are changing positions here. So that guy is oscillating here. Typically in USA is about around 60 hertz. It's like even around the world about between 50 and 60 hertz. That's the frequency of the oscillation of that AC. So and if it's oscillating, oscillation motion is can be represented using wave form. Is that okay? So what that is saying is that our voltage, for example, let's begin with the voltage. So it means that this point is the maximum voltage that we can generate, or this point, maximum voltage that we can generate. So if you remember vividly, it corresponds to what? Our wave equation, where we have that this is the amplitude or maximum upward or downward displacement. So that's the maximum voltage that could be generated. Now, so we call that value V max or Vm or V sub naught. Typically in most textbooks we use V naught. So I'm going to here forward use V naught. So V naught is given is the peak voltage, and of course I naught or I max what? Peak current. Peak current. And so it is possible for us to calculate, just like it is possible for us to calculate the vertical displacement of a particle in wave motion at a particular time as A sine theta. We can also calculate the instantaneous, we call that instantaneous voltage or instantaneous current of the at a particular time in the circuit. Is that okay? So that is current at a particular time. We call it instantaneous. So in some textbooks you see for voltage V sub t or just V. Is that okay? Voltage at a particular time. That will be giving us the same way we have this, that A sine theta. In my video on waves, I've discussed how we generate this. So in order to conserve time, I will not be regenerating this again. But from here, you see the amplitude is corresponds with amplitude here. So it's going to be peak value sine theta. So we have V sub naught sine theta. Is that okay? And recall that theta is equal to omega t. And recall also that omega t is equal to 2 pi f. So we can therefore say that V is also equal to V sub naught sine omega t, or V equal to V sub naught sine omega. Omega is 2 pi f, so it becomes 2 pi f t. These are three possible equations that we can use to calculate our instantaneous voltage at a particular time. So for example, voltage at maybe here 1/4 or 1/8 the cycle, or 1/4 the cycle, or half of the cycle. So we want to calculate the voltage. This is the formula that we use. Okay? Now, we also know that if this is the case for voltage, since voltage and current alternate, then it means that instantaneous current I will be equal to I sub naught sine theta. The same way, then I will be equal to I naught sine, since theta is omega t, then we have this, and I equal to I naught sine 2 pi f t, since omega is 2 pi f. Okay, now we have this. Now, how do we use, so it basically makes sense to say that we use all the values that we use in discussing, the parameters we use in describing a wave motion to also describe the alternating current motion. Okay. Now, because current and voltage are alternating between maximum and minimum value all the time at a particular frequency, it is almost impossible to it is possible to calculate the peak values, but it's um, not if you try to take the average of both minimum values as the effective value of the voltage, what you keep getting is zero. So scientists devised a means to calculating that, and they called it the root mean squared value. The root mean squared. So for the root mean squared value of voltage or current, we call it IRMS. Is that okay? So we say RMS value, root mean squared, that's the meaning. And V, we call it VRMS. So how do they calculate the IRMS? Now, the IRMS is calculated using the formula I sub naught root over root 2, or since root 2 is 1.40, by the time you do the math, you are going to get that is I sub naught times 0.70771, I think. So then the same way here, VRMS is going to be V naught over root 2, which will mean V naught times 0.7071. All right. Now, but what by definition, what does this mean? By definition, it means that it is now since this voltage is oscillating between maximum and minimum value, the value is not the effective voltage. For example, the effective voltage through across a component will not be the maximum value. The effective voltage, because it's oscillating between maximum and minimum, so it means it is oscillating between two maximum values. So it is going to be at some point less than the maximum value, at some point very insignificant time anyway. It's going to be less than the maximum value in between the cycle. Is that okay? So it is only at the end of the cycle that it always attains what? Maximum values. So now, if that's the case, then it means that it is not the maximum value of the voltage that is effective throughout, through a given component. So we call this IRMS the effective value. Is that okay? Or the way it is defined is that is the amount of current, IRMS, or root mean squared current, is the amount of current that will dissipate as much heat as would a DC circuit. So what that is just saying is that if it were running in the direct current, so it's not oscillating between two values, that the amount of current that this thing would have dissipated, the amount of current that would have run in the system is equal to the IRMS value. So keep in mind that therefore, since IRMS and peak values are not equal, peak value is always greater than IRMS in your calculation. Take note of that. The difference will not be so much. Is that okay? The difference will not be so much. Right. So, and it is this IRMS value that the oscilloscope or ammeter, the oscilloscope can be used to measure the voltage or current across the circuit, AC circuit. So the oscilloscope measures the RMS value. Is that okay? The oscilloscope measures the RMS value, the effective voltage across the electrical component. Okay. Now, in an AC circuit, we could either, the following components are possible to be connected. We could either have a resistor alone connected. If you have a resistor alone connected, we'll call it a purely resistive circuit. A purely resistive circuit. Now, in a purely resistive circuit, all we basically have is what? Is a resistor, then our alternating voltage. Is that okay? So the voltage across this will be measured using a voltmeter. The voltage across the resistor, across the resistor, we measure using a voltmeter. So this is our resistor. Now, in this kind of case, we say the circuit is purely resistive. And in a purely resistive circuit, the following are obtainable. Number one is the fact that the current and the voltage are in phase. Current and voltage are in phase. In phase means that none is lagging behind the other. So if we have the current go like this, then we have the voltage go like this. They are perfectly in sync. Is that okay? So if this be the current, this will be the voltage. Does that make sense now? So we know that both of them are in phase. Or another vector diagram we use is this. So we say this will be the voltage, this will be the current. Is that okay? So they are in phase. So it means that they are in the same distance in a circle. They are in the same position in a cycle. So they are moving here. If they are moving like this, this means that they are at 90 degrees at the same time. Half of the cycle at the same time, 3/4 of the cycle at the same time, and of course they have completed the cycle at the same time. So we say the current and voltage are in phase in a purely resistive circuit. So it therefore means that if I want to calculate the effective voltage here, so let's just use, we could use V or V effective. Now the effective voltage or V effective here is given as the current RMS value of the current that is passed through the resistor, or the effective current through the resistor times resistance of the resistor. Does that make sense? The effective voltage is the IRMS value. We call the effective voltage to VRMS equal to IRMS times R. That means that I want to get the peak value. The peak value will be equal to what? The peak current times resistance. I hope that makes sense. Peak value of the voltage, what? Peak value of current times resistance. But make sure to get the fact that the vector diagram, the resistor, the voltage, and the current are in sync. They are in phase in a purely resistive circuit. All right. So what that means in a purely resistive circuit is that the only opposition to the flow of current is offered by a resistor. Okay. Now let's go to another component of the AC circuit. Could be a capacitor connected in series. So for a capacitor, we call it a purely capacitive circuit. In a purely capacitive circuit, we are saying that it's only a capacitor that is connected in series. Only a capacitor is connected in series to the AC voltage. So, and the voltage across the capacitor will be measured using a voltmeter. So, now what this is also saying is that in a purely capacitive circuit, we have only a capacitor, and we know that in a purely capacitive circuit, this is obtainable. As the voltage is trying to pass across the capacitor, one thing that happens is that the capacitor stores charge, isn't it? So voltage will be delayed. Does that make sense now? The voltage will be delayed because it will be stored on one of the plates first. Is that okay? To be stored on one of the plates, there will be higher potential on one plate than the other. Is that okay? So as it is being stored, because it is being stored for a while, the current will lead voltage by 1/4 of a cycle. Or I will say the voltage lags current. Lags means it is behind, lagging behind. It will lag behind the current by 1/4 of a circle is what? 1/4 times 360, which is what? 90 degrees. Does that make sense? Okay. So, and if that makes sense, then it means that the voltage through the capacitor is going to be the effective voltage, the effective current, which is IRMS current through IRMS through the capacitor, the current across the capacitor, times the, now this is times the opposition to the flow of current due to the capacitor, and that is called reactance. It's called what? Reactance. So resistor offer an opposition that is called resistivity or resistance rather, resistance, while the capacitor and inductor individually offer an opposition known as reactance. We denote it by X. Is that okay? Reactance is denoted by X. So if it is reactance due to the capacitor, it will be called capacitive reactance. capacitive reactance. That is, the opposition to the flow of current due to the capacitor is called capacitive reactance. So hence we have V sub C is equal to what? The effective current across the capacitor, not the peak current. So the voltage through the capacitor will be the IRMS value times the opposition to the flow due to the capacitor, X of C. But I've not given you the formula for X of C. So let me give you the X of C value will be given as, we have not been labeling our formulas, but try to label in your notes. Is that okay? Just label as you deem fit. You can say 1, 2, 3 formulas for each case. So X of C is given by the formula omega 1 over omega C. Is that okay? Where C is the capacitance of the capacitor. Capacitance denoted is measured in farad. Of course, we know resistance is measured in ohms. Resistance is measured in ohms. This guy, reactance, is also measured in ohms because it's an opposition. But we only gave it a different name because it is not the one offered by resistance. It's the one offered by capacitor. So that's why it's given a different name called reactance. Here, capacitive reactance. So recall again that omega is equal to 2 pi f. If that be the case, then X of C will become 1 over 2 pi f C. So, and that's the equation for this guy. So after getting X of C value using 1 over 2 pi f C, then V sub C now becomes IRMS times what? IRMS times or over 2 pi f C. So that is one other formula you can use. Now, listen carefully. We are not done with the generation of formulas. There is something again. Since we say that in a capacitive circuit, the current will always lead the voltage by 1/4 of a circle, then it makes sense to say that the current, instantaneous current through the guy will be equal to I sub naught sine theta, sine omega t. If this is the case, then the voltage, instantaneous voltage, who is leading here? We said the current is leading. If the current is leading, then voltage will be V sub naught sine omega t minus pi over 4. Or, and pi over 4 means 1/4, and pi over 2, because pi is 180. Pi over 2 or minus 90 degrees. Or V naught sine omega t minus pi over 2. I hope this makes sense to you, because this is minus 90 degrees because it is lagging by 90 degrees. The voltage is lagging by 90 degrees. Or another way to write that will be that since current is leading, then current, instantaneous current will be equal to the current at the peak current sine omega t plus pi over 2 if voltage is equal to V sub naught sine omega t. So if voltage is V sub naught sine omega t, then current will be I naught sine omega t plus that 90 degree by which it leads the voltage. I hope that is clear. Okay, now let's go to a purely inductive circuit. So the third component that we can add, so this is the second component. The third component that we can add to the AC circuit is the inductor. So of course, you know that would generate what? Self-inductance, isn't it? So the opposition, so we say the circuit is purely inductive. Purely inductive. Is that okay? I don't need to write that again. So there's going to be an opposition to the flow of current here too, and that opposition of that is known as inductive reactance. So the way we define reactance is that it's the opposition offered to the flow of current in an AC circuit due to a capacitor or an inductor or both. Capacitive reactance is defined as what? The opposition offered to the flow of current due to a capacitor or an inductor or both. Please, if you have been enjoying the video so far, please do well to subscribe to the channel. Just do well to subscribe to the channel and share the video with your mates. All right, so, or people that you see needs it. Now, needed people. So, inductive reactance, as I said, Now, so let's analyze the same way we did here. This is an inductor, and of course, these are AC source. So current is going to alternate, and then the voltage across this is going to be given as V sub, let's call it V sub L. Since this guy is V sub C, then the voltage across this guy is going to be the effective current, which is always IRMS. That is the effective current after alternating between maximum values, the effective current that we can record times X sub L. But we've not given the formula for X sub L. What is X sub L? Inductive reactance. We denote it as X sub L. Remember, capacitive reactance is what? X sub C. Capacitive reactance, X sub C. So here, inductive reactance, X sub L, is given by the formula omega L. And if this is the case, omega is 2 pi F, so 2 pi F L. So this is the formula for capacity inductive reactance. If this be the case, then we know that V sub L will be can be equal to IRMS times 2 pi FL. That's one formula. Now, one thing that is noticed in an inductive circuit, a purely inductive circuit, is that here it is current that is leading voltage. In this case, because the inductor will generate self-inductance, which leads to what? Eddy current. What will happen? Eddy current is going to flow in the reverse direction of current, isn't it? So making current to do what? To lag. Does that make sense now? So current will lag the voltage. Current lags voltage by 90 degrees, or the same 1/4 of a cycle. So, or the voltage leads. In our 5 days of physics, I've given you the trick to knowing that. For those of you that normally forget it, you know inductance, L is given by L is the inductance. I didn't mention that here. L in this formula is known as inductance. And it is measured in Henry. Inductance is measured in Henry. Okay? So now if you want to remember which one leads or which one lags, so I'm sorry, like I said, so for those of you that normally forget, since we have said that voltage leads current here by 90 degrees the same way, or by pi over 2. Now, for those of you that normally forget, just remember that inductance is L. So an L is like V, right? L can be written like V. So voltage leads here. Then current, capacitance, C, current. Does that make sense? So current leads in this case. Just remember the ones that leads. You remember the leaders, you remember the laggers. Is that okay? So that is how to remember it. Or that is how I remember it. You know. So now if this is the case, then it makes sense to also say that the instantaneous current in this guy, in this across this circuit, is going to be the peak current sine omega t. If current is the lagger, then I naught sine omega t minus pi over 2 if voltage is V naught sine omega t sine omega t. So here it's showing that voltage is the leader. Voltage is the leader. Voltage is leading. Does that make sense? Or we can write this as V equal to V sub naught sine omega t plus pi over 2 if current is actually I naught sine omega t, since current is the lagger. I hope that is clear. So this is showing you that voltage is ahead by pi over 2. Okay, then I failed to draw something, so please come back with me. You remember the vector diagram we had for that guy? In this case, we need a vector diagram for the velocity, for the voltage too. So in a purely capacitive circuit, I repeat, a purely capacitive circuit, who is leading? The current is leading. So if current is leading, then it means that the voltage will be below here. Since it's leading by 90 degrees, then current will be ahead by 90 granot. So this will be current across the capacitor, or effective current, or IRMS across the capacitor, and this will be the voltage across the capacitor. So this is the vector diagram. Is that okay? This is the vector diagram. Now, how about in an inductor? In the case of purely inductive, who is leading? The voltage here is leading. So voltage is going to lead by 90 degrees, while current is going to be here, IRMS or I sub L. I sub L because it's the current across the capacitor. Then V sub L, voltage across, the inductor rather, voltage across the inductor. So voltage is leading by 90 degrees. Is leading by 90 degrees. Is that okay? So this is the vector diagram that represents that. Now, what if we now add a resistor to both of these, or maybe not really a resistor? What if we add both of them together, a capacitive and an inductive circuit at the same time? So we call that an LC circuit. LC to represent what? Inductor and capacitor, a current, a circuit that has inductor and capacitor connected in series. That's not LC. L representing inductance, capacitance. Is that okay? So in that case, what we're going to have is something like this. We have our inductor connected in series with our capacitor, and so what happens is that current is going to flow. Okay, so the same thing applies. Now, only that in this case, you remember that in the vector diagram, in purely inductive, who will lag and who will, in a purely inductive circuit, current, in purely inductive, current will lag. So if current lags, voltage leads, V sub L. Purely capacitive, current leads, voltage lags, V sub C. So what happens? Then it means that the effective voltage here, will just be the vector. This is just subtraction because this looks like two forces. Do you remember equilibrium of forces or net force when we did that in mechanics? Simple. We know that we did that. If this was a load and F1 was acting here, F2 was acting here. Let's say 100 Newton basically was acting here and 20 Newton was acting here. This guy, this body will move where? Towards this direction by what? 80 Newton. How did we get 80 Newton? 100 minus 20. So the same way, because they are vectors, then we'll have that this guy, the vector, the effective voltage is going to be V sub L minus V sub C. Okay? So if that's the case, then, you know, other things apply, like this is the basic formula you need for your voltage. This is the formula you need for your voltage. V L minus V sub C. And we already got how to get V sub L and how to get V sub C. Okay? And that's the vector diagram there. One will be going down, the other will be going up. So, but of course, we usually have it in this convention because the VL is always assumed to be positive and the VC assumed to be negative. So it's going to be, as in the point is going to be lower than this, so we always subtract. The idea is just subtract it. It could be negative, negative. Is that okay? Just subtract because they are going to be at 180. So the phase difference between them is what? 180 degrees between across. Look at it, phase difference is going to be what? 180 degrees. Does that make sense? Okay. So that's that about that. Now, what if we now had a resistor and a capacitor alone? So we call it RC circuit. What if we had a resistor and a capacitor? So in that case, you're going to have your resistor, then you have your capacitor. Okay. So notice that I changed the. You could use this to represent resistor, and you could use this to represent resistor. In case you are wondering why I changed it, because I don't think this is what I used initially. Okay. So these are voltage source across the RC circuit. In this case, the opposition to the flow of current will be from two guys, from the resistor and from the capacitance. Once a resistor is introduced with another component, the opposition does not become resistance alone. The opposition to the flow of current becomes impedance. It's called what? Impedance. Impedance is denoted by Z. Is that okay? So we define impedance as the opposition to the flow of current given by a resistor and a capacitor, or a resistor and an inductor, or a resistor, a capacitor, and inductor all together, all three connected together. So that's the impedance, Z. Okay, now in this kind of circuit, the Z, now in this kind of circuit, remember that in a purely capacitive circuit, voltage will lead. Current leads in purely capacitive. So if current is leading, it means voltage is lagging. Then purely resistive, current and voltage are in phase. So current and voltage are in phase. So V sub R, that is voltage across the resistor, but here V sub C. So it means that the effective voltage will be around, will be the vector of this, or sometimes you can draw it this way, that is, this will be the V across both of them. So you can take the vector sum of this guy, so that V will become what? You remember that since it's a 90-degree Pythagoras case, so we can use Pythagoras in a rectangle, it's a triangle rather. So the vector diagram of this is going to look something like this, basically. Is that okay? Where this is V sub R, V sub C, and V, effective voltage. So the effective voltage here will be V squared equal to what? V sub R plus V sub C. That squared, is that okay? That becomes V equal to the square root of V sub R squared plus V sub C squared. Okay, so that's value of the effective voltage. Now, of course, there's going to be an angle between them called the phase angle, phi. So the phase angle is given by so you can calculate the phase angle in this case, phase angle by tan phi equal to, tan is opposite over adjacent. So that will be V sub C over V sub R, where phi is what? Phase angle. Phase angle. And of course, we can also calculate power in this system. Power is that okay? Power will be equal to IV cos phi. But this case is the effective voltage. Is that okay? And current will also be effective current, which is what? IRMS. Is that okay? Cos phi. Okay? So cos phi here is known as the power factor. It's known as what? The power factor. Cos phi is a what? A power factor. And cos phi is given by, what is phi? Adjacent, cos rather. Adjacent over what? Hypotenuse. Adjacent over hypotenuse. So what's the hypotenuse? V. So that becomes V sub R, which is adjacent, over hypotenuse, which is V. Is that okay? And in this case, the current, since it's in series, the effective current, IRMS, will be the same in both resistor. So it will be IRMS times, what is formula for voltage? Voltage equal to IR. Is that okay? You remember that from Ohm's law. So IRMS times R over V will be IRMS times, now V here is going to be equal to, V here, I didn't derive that though initially. I'm going to derive that. Let me show you something. So you already got this, right? Okay. So V here, since here we have that V squared is equal to VR, so the voltage across this V here is going to be V squared here is going to be IZ. Does that make sense now? IZ. I squared. I here is IRMS. Keep in mind, so I'm just not writing it. Voltage, the effective current. And here is going to be IRMS because they are connected in series. The same current will flow, remember. The same current will flow because they are connected in series. Current is the same. So I, in this case, R, the resistor, plus here, I, X sub C, all squared, all squared. So if that be the case, we can divide through by I squared. You know how I got that, right? Voltage, effective voltage will be I times the impedance. So, and this is current voltage through the resistor, across the resistor, I times R, and voltage across the capacitor, I times X of C. Remember from what we have derived so far. Okay, so this now becomes, this takes care of all of this, and then we have our Z, which is impedance value, will be equal to what? The square root of R squared plus X of C squared. Okay, so mathematically you can derive the Z this way. So this now becomes cos phi will now be equal to what? IRMS. We'll cancel IRMS. V will be I sub Z. Do you understand now? I sub Z. I times Z rather. So cos phi can be given as what? R over Z. I hope that makes sense to you. Okay, and if you do not get it, just try to, derive it again. Derive it again. Or just follow what I did. It's very easy. It's very easy. Now, the other kind of circuit we can have is the one that is called the RL circuit. RL circuit. So, and of course, in an RL circuit, here's what we have. In an RL circuit, we have the resistor connected in series to an inductor. So that if this be the case, so this is our resistor, this is our inductor, so that if this be the case, of course, I've told you that the opposition to the flow of current will also be called what? Impedance. I've told you the impedance is the opposition offered by the resistor and a capacitor, or the resistor and an inductor, or the resistor and the inductor and capacitor, the three components together. All right, but majorly it is when the resistor is connected. If it was just inductor, there will be no opposition given that way. The opposition will not be called impedance, but in this case, it will be called reactance. It will be called reactance. So what we have therefore is that impedance is also denoted by Z in this case. Is that okay? So let me show you the vector diagram also, since in a resistive circuit, voltage will be in sync with current, but voltage we said will be in sync with current. But in an inductive circuit, voltage will lead current. So it means that voltage also leads. So V sub L also leads V sub R. Is that okay? V sub L, voltage across the inductor, also lead voltage across the resistor. So the vector of both, or it will be in this direction, the vector of both is going to be the effective voltage. So, and of course, you want to take vector there, it becomes V squared equal to V sub L squared, or V sub R first, squared plus V sub L squared. So if this is the case, what's formula for voltage here is going to be what? Current times, that's RMS current times the impedance. Is that okay? The impedance, which is equal to the voltage across the resistor, IRMS again, times the resistance of the resistor, plus IRMS again, times the X sub L, that is inductive reactance. By the time you can square all this, By the time you divide through by I squared, you have that Z squared is equal to what? R squared plus X sub L squared. Of course, Z equal to square root of R squared plus X sub L squared. So in like manner, V is going to be equal to the square root of all of this. All right. So the same way, in this case, the phase angle is going to begin at what? Tan phi. So phase angle here is going to begin as tan phi, which is what? V sub L, the same procedure. V sub L, V sub R, sorry. No, it's V sub L, sorry. V sub L over V. That makes sense. Do you understand now? Because it's between this guy and this guy. Tan, opposite V sub L over adjacent V sub R. V sub L over V sub R. And what is V sub L? Oh, no, that's basically the formula. So like you can begin to introduce other things, you know, because V sub L, the current will be the same, IRMS over V sub R, IRMS. But in this case, it will be X sub C times what? X, V sub R will be IRMS times R. So this takes care of this. So it means the formula can also be what? X sub C over R. In this case, it can also be what? X sub C over R. Here, X sub L, sorry. That will be the inductive reactance. You want to come inside? Come now. So that's the case here. That's the case here, basically. So then we can therefore have that the power factor is going to be cos phi. Does that make sense? And remember that power is already IV. So this becomes IV cos phi. But in this case, the V is going to be the effective voltage. So, and cos phi here in this case, cos is adjacent, that is V sub R, over hypotenuse, that is voltage, effective voltage. So that means that since the effective current is going to be IRMS over IRMS, for these two cases, V sub R is going to be IRMS times resistance, V will be IRMS times the impedance, then therefore means that power factor is always R over Z. Power factor is always what? R over Z. I hope that makes sense. Okay, then the last case is a case where we have both the resistor and the capacitor and the inductor connected in series. So if you have that kind of case, then we have this. So if we have all of the components connected in series, we have RLC circuits, that's what it's called, the RLC circuit. So in the RLC circuit, what we have is the resistance, the inductor, and the capacitor connected in series. So what we're going to have is this resistor, the inductor, and the capacitor connected in series. I'm just trying to shorten it. Okay, so if you have this as the case, then you will have that impedance is also going to be the opposition to the flow of currents. The impedance is also the opposition to the flow of current, impedance Z. Okay, now, but in this case, there is something different. There are three components. So the voltage in the inductor will lead the current, but in the resistor to be in sync with the current. But in the capacitor, it will lead the voltage. Does that make sense? That is, the current will lead the voltage in capacitor, the voltage and current will be in sync for VR, and the voltage in the inductor will lead the capacitor, will lead the voltage in the will lead the voltage in the resistor. So it means V sub L will lead V sub R. If that's the case, therefore, then we know that V sub L, the vector of this case, is going to be the effective voltage across here is going to be V. And V in this case is going to be V sub L minus V sub C. That will be the voltage in the, if you want to resolve the vectors in the y-axis. So that's going to be like that. Then the voltage in the x-axis is going to be V sub R. So, and that makes sense. Then the vector is going to be like this. V is going to be the vector. So the effective voltage here is going to be equal to V sub R. Now that is this squared times this squared plus V sub L minus V sub C all squared. So if that be the case, then this guy is now the effective current the same way, IRMS dot Z all squared is equal to V sub R squared is going to be IRMS Oh, yeah. IRMS times the resistance all squared plus. Now, in this case, we're going to have V sub L is going to be IRMS V sub C, that is X sub C rather, minus IRMS X sub L. No, the X sub L first rather, minus X sub C all squared. So if that be the case, if we divide through by IRMS squared, because it's common term here, so we're going to have Z squared equal to R squared plus X sub L minus X sub C all squared. So if that be the case, then the impedance is going to be the square root of R squared plus X sub L minus X sub C all squared. Do you understand? Oh, you understand? Okay. All right. So in this case, therefore, we have the phase angle. The phase angle, of course, here is going to be tan phi again, and tan phi is going to be equal to, what is tan? Opposite over adjacent. So what's the opposite here? V, no, opposite. The guy facing the angle is the opposite. That will be V sub L minus V sub C over, what's the adjacent here? V sub R. Okay, so this is going to be the value, and that makes sense here. Okay, so that is that. That is that. I mean, of course, you can decide to derive further and say that it's going to be, since current to be the same in all values, then the X sub L, which is the inductive reactance minus the capacitive reactance over the resistance. So that is going to be the phase angle. And of course, the power factor here, I'm going to rush because I have to rush. So the power factor here, of course, the power factor here is going to be cos phi also. Cos phi. So what is cos phi? The cos is what? Adjacent over hypotenuse. So here, that's what? V sub R over V. God bless you. So then we have R again over Z. That makes sense. Okay. Now the last case with simple AC is the case of resonance. It's the case of resonance. Now in the case of resonance in an AC circuit, it is resonance occurs when the X sub L value is exactly equal to the X sub C value. And the X sub L value, we remember that it is omega L. And this guy is 1 over omega C. If that be the case, then omega L will become 2 pi FL is equal to 1 over 2 pi FC. And if that be the case, we can cross multiply to try and get the resonant frequency. So by the time we cross multiply, we're going to have this by this, 4, pi times pi squared, F by F squared, L by C, LC equals 1, yeah? So you now divide both sides. You want to make F subject. Divide both sides by what? 4 pi squared LC over 4 pi squared LC. This takes care of this, this takes care of this, do you get it now? So we now have F squared equal to 1 over 4 pi squared LC. Yeah. I have accidental students, so that's what I'm talking to. So we have the square root of this to get F, and that gives us what? F equal to square root of 1 over square root of 4, 2 over square root of this, pi over square root of this, LC. All right, so resonant frequency is going to be given as by the formula 1 over 2 pi root LC. And this makes sense because let's not talk about why it makes sense. In my COP series, I'm going to be talking about why it makes sense. But of course, we can also get angular resonant frequency. Angular resonant frequency. Because we can abstract this guy to this side. So it becomes 2 pi F equals 1 over root LC. And remember, 2 pi L is omega. So that becomes 1 over root LC. All right, God bless you. If you stuck till the end of the video, do want to subscribe to the channel and click the bell notification. And of course, share the video with your friend. God bless you as you do so. Thank you.